Hello and welcome. This is Cambridge O-Level Physics paper number 4, alternate to practical. The subject code is 5054. This is May-June 2021 exam, and this is the variant 2 for this offering or this exam. So let's start. The first question, it says, a student investigates how the potential difference V across a fixed resistor R changes as extra resistance is added to the circuit. Part A, first point, she sets up the circuit as shown in figure 1.1. She connects the crocodile clip C to the point on the resistance wire at length L equals to 20 centimeters from end X. She closes the switch. She reads the voltmeter, records the reading. She opens the switch. Figure 1.2 shows the voltmeter reading. Read the voltmeter scale, and in table 1.1, and in table 1.1 on page 4, record the voltage V. Okay, so first point, so as we see, the voltage over here is the scale between 1 and 2 is of 10 points, so 1.1, 2, 3, 4. So potential difference is 1.4 volts. Then it says, find out the value of 1 by V, and the values over here are two significant figures. So if I'm going to find out the value of V, it will be 0.71. Okay, so this is the value for two significant figures. Then part 2, calculate 1 by V and record its value on figure 4 to appropriate number of significant figures. So looking at the other readings documented in the table, we can easily see that all the values which are recorded are given into significant figures. So we'll use the same convention which the examiners are using, you can say. Then part B, she repeats the procedure in A using the values length equals to 30, 40, 60, and 80 centimeter. Her results are shown in the table 1.1. So these are the results across what she has measured. So just why the student opens the switch between the readings. Okay, so remember, if we see the circuit, so there is a cell. It's not a big source of battery or anything. It's just a cell. So if she keeps the switch connected, it will discharge, and or it will lose some of its potential difference. So when the next time she'll be measuring the reading, it won't be giving her the same potential as it was giving earlier. So she's basically conserving this, you can say, voltage of the cells, or you can say that the cell is powerful enough. In that case, if the cell keeps on, so this wire is having a certain resistance, and with the flow of current, the wire will start to heat up, and with the change in with the heating of the wire, or with the change in temperature of the wire, the resistance of the wire changes, and eventually we'll be getting different answers. So let's see what we have or how we can write it. So this is a 1.1 mark answer. So any one of the reasons would be fine. So why the student opens readings? You can say this avoids unnecessary discharging of the cell. Thus, it keeps the supply voltage almost same for all the readings. This can be one reason. So, or second reason can be this avoids heating up of the resistance wire which causes change in resistance, causes change in resistance. So this is these are two reasons, because we know that resistance is directly proportional, or there is some, again, material to material, there is a variation of resistance with respect to temperature. For example, if this material is made up of any material that is used in thermistors, so the resistance is inversely proportional to the temperature in that case. So this is how, I mean, these 2 points can sum up this thing. But again, first point is a um, relatively more sought after answer for this course, for this question. So on so next part C, on the grid provided in figure 1.3. So this is the grid we are given. Uh, Again, page 5. So I have basically made slides for it, so it's not page 5 over here. Plot the graph of 1 by V on the y-axis. So 1 by V is on the y-axis and length L on the x-axis. Start the axis from 0, 0, draw the best fit straight line. Okay, let's try it. So this is the table we have. So we are plotting this on the x-axis and this part on the y-axis. Okay, so if we see our length, the length is varying from 20 to 80. So you can say on this graph, we can give it a 10-point margin: 10, 20, 30, 40, 50, somewhere here, 60, 70, 80, and this is, so x-axis. On x-axis we have length in centimeters. Remember this. Then we have y-axis, and when we see our 1 by V values, let me go back. 1 by V values, so something between 0.71 to 1.3, the values are varying. So let's see. So we have a total of 1, 2, 3, 4, 5, 6, 7. So we have 7 good solid blocks, and we have technically 8 lines. So what we can do is give a margin of 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4. So we'll be good like this. So 0.2, 0.4, 0.6, 1.0, 1.2. Oh, sorry, this is 0. So I have missed 0.8. So again, make sure that you don't make such mistakes in your exam. So this is 0.8, this is 1.0, this is 1.2, this is 1.4. Again, this is our y-axis, and on the y-axis we have 1 by V, and units are volts minus 1. Okay, so labeling is again very important. Label your axes properly, labeling the axis properly. Then what it comes is that we have to find draw the line. So for 20 centimeter, let's plot the point. For 20 centimeters we have 0.71. So 0.71, 0.7, and somewhere here is the value for 20 centimeter. Okay, then for 30 centimeters we have voltage of 0.77. 30 voltage is 0.7. 2, 4, sorry, 2, 4, 6, 8, and somewhere here. So on 20 we have some value here. Then on 40, sorry, on 30 we have here. On 40 we have 0.91. So 0.91. So this is 0.9. So somewhere here is my value for 40. Okay. No, man, I do not want. So 40. Then on 60 we have value as 1.1. So 1 is here, 1.1 is somewhere here. So on 60 I have this value. On 80 I have the value of 1.3. So 1.3 is, this is 1.2 somewhere here. This is my 1.3 value. So we have to basically make a best fit straight line. So if I'm going to make a best fit straight line, what I have to make sure is that my points are evenly distributed on the line and my line is passing through maximum number of points. So let's see, if I'm going to miss this one, I have to miss the upper one. So make sure that the next two lies on the point line. So my line would look something like this. Okay. And I extend it back and say somewhere, sorry. So let me, so this is so for example, my line would look something like this. Okay, so this is how my line looks like. Okay, so let's go ahead. So it says in part D1, calculate the gradient n of your line, show the working and indicate the on the graph the values you use. So remember, gradient is change in y, delta y by delta x. Okay, so let's see. So when you have drawn this line, make sure you use you first of all give 2 points on the line and you use those 2 points to find out your value. So let's see what points we can use. So I can use, say, this point, I call it point B, and I go back and I can use this point, say this is point A. So for point A and point B, if I use, they both match at A, point C. So my gradient from here is delta y by delta x. So point B, say, let's say on the x-axis, point B is 50. And on the y-axis, point B is, say, 1. Okay. And on the coordinates of A, let's say the value of A is this. So A is 25 here. And on this side, A is something 6, 7, 7.2, 7.4, something around 0.75. Okay. So I mean, when you'll be drawing this graph, you'll have much more accurate values. Okay. So I have the coordinates of both. So change in y will be 1 minus 0.75 and change in x would be 50 minus 25. This will be 0.25 divided by 25. And this is the value of m. So m will be, let's calculate. So it will be, I think, 0.01. But it's good. 0.25 divided by 25. So 0.01 will be the value of m. Okay. So this is how we calculate, and make sure you mention these 2 points on your graph. So over there we go and we do 1 minus 0.75 divided by 50 minus 25. This comes out to be 0.25 divided by 25, and this value is 0.01. Okay, and remember, this is 0.01, and the units on the y-axis we have volts -1, and on the x-axis we have centimeters. So it will be 0.01 1 by volts centimeter, something like this. So slope 0.01 and the units are 1 over volts dot centimeter, something like this. It be your correct answer. Then it says extend your line until it crosses the y-axis, measure thus intercept C on your line makes with the y. So we extend it back and we found out that it meets some point here. So this is intercept C, and this value comes out to be something around 0.5. Okay, so moving ahead, so C is 0.5, the units are 1 by volts. Okay, so this is how you write it. I mean, you can ignore the units as well, but it's good practice to write the units as. So calculate the electromotive force E of the cell using this equation. So the value of K, and K is given as 1 and divided by 0.5. So the 0.5 is the value over here. So this comes out to be 2 volts. So 2 volts. So the answer is 2.0 volts, and this is how you're going to, again, you will be having a little different values depending upon what results you get based on your graph. But just make sure that when you're drawing the line, your points are evenly distributed on the line. Make sure you have maximum number of the points coming on the line, and if there is 1 point above the line, make sure you leave 1 point below the line. Okay. Then part F, it says, suggest one practical reason why, despite carrying out the experiment with care, the student value of E may not be the true value. So the key reason, there may be many reasons. So one is the cell discharges with time, and this causes the error in our readings. Then we are not considering the internal resistance of the cell. There may be some zero error in the voltmeter which may not have been seen. There may be poor connections of wire. With time, the wire is heating up, with the resistance it is heating up. So there are many reasons. So for practical reason, the easiest one is, where is my pen? The cell discharges with time, and this causes error in the measured readings. Other reasons, internal resistance of cell is not considered, poor connections. For example, the crocodile pen clip is not properly connected. Zero error adjustment. Okay, you can say heating of wire, and things like that. So these are all good practical reasons. Anything you can write amongst these will give you good complete credit. My choice will be to go for the reason that suits the best for me. It's like that the cell discharges with time, and it loses its potential difference or the stored energy, and this causes a readings. Every reading comes out at a different voltage level, so that's why when you're measuring something like that, it comes it gives a faulty results. So part G, it says the results in table 1.1 show that the length L of the resistance wire increases, the potential difference decreases. The result state how the results show that length is not inversely proportional to V. So remember, if something is inversely proportional, for example, length is inversely proportional to 1 by V, it means that the length is equal to K times a constant that is equal to 1 by V, and length time V is equal to that constant, or that constant V. So but when we are seeing the product LV over here, for example, the best way to see is this. So multiply this thing, the LV, the product LV. So we just keep on multiplying these values together. So first case, 20 multiplied by 0.71. So it comes out to be 14.2. Then 30 multiplied by 0.77. Sorry, 30 multiplied by 0.77 comes out to be 23.1. Then comes out to be 40 multiplied by 0.91. So LV is 36.4. Then 60 into 1.1, 60 into 1.1, 66. And then comes 80 multiplied by 1.3. Oh, sorry. So this is the wrong product I'm taking. So just multiply it with V. I'm multiplying it with this. So I apologize for that. So 20 into 1.4, basically 20 multiplied by 1.4, it comes out to be 28. Then 30 into 1.3, 30 into 1.3, 39. Then 40 into 1.1 is 44. 60 into 0.9, 60 into 0.9 is 54. And 80 into 0.8 is 64. So we can see that the product LV is not equal to constant or any constant. So this is the reason one. You can say the other reason is that when we're looking at the graph is in the form of y equals to mx plus c. Okay, so it is intercept, it is having an intercept, so it means that it is not linearly proportional. So how it is not inversely proportional? So first of all, the best answer is to say the product of length to V is not a constant value as shown in the column drawn on the table 1.1. It can be one reason. Number two, inversely proportional graph. The graph doesn't go through the reason. The graph is not going through origin. So it's the best answer is these. I mean, based on these graphs, you can easily say that that the length of the wire is not inversely proportional to V. And the reason or a practical reason is that there is actual physical resistance R that is available in the circuit, and that this R and this voltage is basically measured across this R. And this is if we have to say measure the relationship, so this voltage must be measured across this this value of resistance. So technically this voltage is against this resistance, and the variation in resistance is not the variation of the resistance of this game. So this is how this you can say the reason for something like this happening. But again, the easiest way is to use the results shown in the table and the concepts basically that can be inferred from the graph of the uh, given in the exam. Okay, so next question, question number 2, it says the student measures the acceleration of a trolley rolling down a ramp. First point, he makes a ramp by using a wooden plank, resting one end on the plank on a bench, and using a stand and a clamp to support the other end. Okay, he draws the line AB across the across the ramp near to the top. He draws another line CD parallel to AB. CD parallel to AB at a distance 120 centimeter further. Further down the ramp, he adjusts the height of the top of the ramp above the bench by moving the clamp until the ramp reaches an angle of 30 degrees with the bench. He places a trolley on the ramp so that uh, the wheels in front of the trolley touch AB. Figure 2.1 shows the setup of the ramp. So this is his setup. So it has a trolley over here. The ramp is clamped here. AB line here. BC line this angle is 30, and the distance between point B and D is, or the lines AB and CD is 120 centimeter. Okay. So first part, suggest a measuring device that the student uses to ensure that A, B, and C, D are 120 centimeters apart. So remember, measuring tape is the best tool. People will write ruler or a rule or a meter rule, but remember this is more than 100 centimeter. So measuring tape can, be easily, extended, can be long enough, can be short enough. It is more easily portable, and a scale will not give you one in this, or a meter rule will not give you this reading in one set. So the best device would be a measuring tape. Then the RAM makes an angle of 30 degrees with the bench. So device protector, or the D shape tool, which is there. There's a protector can be used to measure this angle. Okay. Then part B, the student releases the trolley at the same time starts the stopwatch. He stops the stopwatch when the trolley has traveled 120 centimeters down the ramp. He places the trolley at the top of the ramp with its front wheels touching AB and repeats the procedure twice. Uh, the times T for the trolley to travel a distance of 120 centimeters are shown. Uh, so just one reason why there is a large variation in these times. The biggest reason is the human reaction error. So as soon as he leaves the trolley and he starts the stopwatch, that is the reaction time is there. And since the trolley is moving down the ramp, it is a fast moving object. So it's pretty much difficult to judge a fast moving object. So again, uh, the student is measuring time for a fast moving object, and in such a case, human reaction time causes large variations in the readings, in the time measurements. Readings. Okay, so this is the best explanation to the cause of this thing. Okay, then part 2, it says figure 2.2 shows a side view of the arrangement of the trolley at the start position. On figure 2.2, draw the position of trolley when it has traveled 120 centimeters. So 120 centimeters, it would be at this point. It is so the wheels would be, the first wheel should be crossing over here. So the trolley would be looking something like this. Something like this would be the uh, location of the trolley. Okay, then it says calculate the average time TAV of the trolley to travel distance. So we are given 3 times. So TAV is 0.7 seconds we are given, when we are given 0.81, and then we are given 0.95, and add these divided by 3, so time average comes out to be 0.82 seconds. So this average time is 0.82 when units are given seconds. Okay, next part, calculate the acceleration A of the trolley down the ramp using the equation 2D. Give your answer to this. So acceleration in is also is in this case is given, distance is centimeters square and time is distance is centimeter and time square. So these are the units, and 2 into D, 2 into 120 divided by 0.82 average time square, and this value comes out to be something 356.93. So we'll use this value, acceleration 356.93, and units are centimeter per second square. Remember, your marking scheme in this question, it says that the value is 360 centimeters per second square. I mean, it's up to you, but the best value is to use the actual calculated value up to 2 decimal places and use the units as such. Okay. Um, then it says part D suggests how the student could modify this experiment so that a more accurate value of acceleration A of the trolley can be obtained. The easiest way is to increase the distance, one, uh, and increasing the distance will allow more time for the student, and in a way it reduces the effect of reaction error. Number two, take multiple readings, use multiple readings, and then use another person to operate the stopwatch, and this will give him uh, two set of readings for time, and that will also decrease the overall human reaction error effect. And the best way is to use some automation to bring some electronics, some IR based sensors here, which are operated in such a manner that when the trolley cuts the IR beam of first sensor, it starts counter, and when it cuts the beam of the second sensor at when the trolley crosses CD, it cuts the beam, it stops the timer, and use that electronics to estimate the time, and that will be giving, but then that will be giving the most accurate value in such a case. So suggest how the student, number one, we can say increase the distance D, which will allow more time to the student to operate the stopwatch, hence decreasing the variation due to human reaction error. Okay. The other is take multiple readings and use another person to take similar set of readings, then take average of both sets. So take average of both sets and use consolidated average. So once you have T average for set one and you have a T average of set two, use T1, use a consolidated average T average as for set one plus set two divided by two. And three, bring some IR sensors and electronics to be, or you can say to have accurate results. So bring some sensors and IR electronics to get some excellent results. But I mean, I would say first and or in a way second option will give him more time and overall reduce the effect of human reaction time. or give him more time to operate stopwatch, and in a way this decreases the overall variation. Okay, so next part, question number 3, it says the student measures the focal length f of a convex lens. She sets up the she sets up the apparatus as shown in figure 3.1. The illuminated object is in the shape of equilateral triangle as shown. The object is drawn to full size. Okay, so this is the object and this is drawn to the full size. Okay. Then she switches on the lamp and places the lens at a distance 20 centimeter from the illuminated object. Then part 2, she says she adjusts the position of the screen by moving it slowly backwards and forward until a sharp image of the illuminated object is formed on the screen. The image of the illuminated object formed on the screen is shown full size. So this is again shown in the full size. Part A, it says state the two differences between the image and the object. So the images is inverted, number 1. Number 2, image is magnified. Magnified, you can also use enlarged. So these are the two differences. Inverted as compared to object, and image is large as compared to the object. Again, also write the overhead. Okay. Then part 2, it says measure the height h0. So remember, measure the height h0 and measure the height h1. So you use a ruler to measure this height. So use a ruler A, 1 point here, and h1b over here. So measure this height h1 and measure measure this height h o dash, you can say this size h0. So if you from using the ruler, you can measure these heights. When I used my ruler, and according to the marking scheme, my values are almost the same, so I use the values which are given on the marking scheme. So it says it is 0.9 centimeters and this is 2.6 centimeters. Okay, so remember, if you are printing out this exam paper, uh, in order to solve it yourself, make sure when you print it out, you the printer you're using, make sure it has the setting is set it to it adjusted to full scale, or doesn't shrink it to 99.95 or percent, and in that manner you'll be getting the best results as what will you can be having in your marking scheme. Okay, so when you're practicing these exams in your home or in your class or wherever you are doing it, make sure you have the printout of this exam in the actual you can say magnification via your printer. Okay, next part. Then part B says magnification of m of the object of the image. Calculate the magnification m of the image using the equation h1. So h1 was 2.9. Oh, sorry, 2.6. So it was 2.6 centimeters, and this one was 0.9 centimeters. So this comes out to be magnification was 2.9. Okay, so 2.6, 2.9. Then it says calculate the focal length of the lens with u equals 20. So f, remember, m magnification is 2.9, multiply by 20. Again, this is centimeters, then this is 1 plus magnification is 2.9. So the focal length will be in centimeters. So the answer comes out to be 114.9. Okay, so this is a very simple, straightforward, a 1+1 sort of a question in this exams, and I hope everybody will be able to do it correctly. Okay, then question number 4, or the last question for this exam, it says student uses a plotting compass to plot the pattern of a magnetic field around a straight wire that is carrying current. The student sets up the circuit as shown in figure 4.1. Notice then the wire is is arranged vertically and passes through the middle of the horizontal card. So remember, this is the positive terminal, this is the negative terminal, this is some resistance that's attached to the wire, and when the switch is closed, the circuit forms, the current flows in this direction. So from the right hand thumb rule, so your thumb points in the direction of the current, so your curled fingers will be pointing towards the direction of the magnetic field. So your magnetic field will be uh, in something like this direction. Okay, something like this direction. So now what you have to do is that you have to use this plotting compass, and you have to see this location and how this thing is working. So the first part, it says describe how the student uses the plotting compass to calculate, to plot the pattern of the magnetic field when the switch is in the circuit is closed. You may add to figure 1.4.1 to help explain your answer as you wish. Okay, first of all, let's see how what we can do. So what we can do is we can bring the plotting compass near this, and uh, this plotting compass will look something like this. So mark uh, the position where the needle of this is pointing. So first of all, this needle is A, then remove say this is the end of your plotting needle. So then mark this as A, and then move the plotting compass at this location or one step ahead. uh, See what will happen. So the plotting compass will, or the plot will be something like this. So mark it as B, then keep rotating it, bring it somewhere here. The plotting compass will plot something like this. So mark again and keep doing it till you reaches the point from where you started, or where you had your initial location, and your plotting compass will be pointing in something like this direction. So in this way you end up or developing one complete circle. And if you want to develop a few more magnetic field circles or magnetic field lines, repeat this say experiment by say moving the plotting compass to the right of the initial circle, or to the to the left of the initial circle, or to the right of the initial circle. So let's try to write this down in words. First part, so it says place the plotting compass on the cardboard as shown. So place the plotting compass on the cardboard as shown. So we can use uh, sorry use this figure as well. So as shown uh, at point A, you can say as shown in A. Mark a point, mark a point at, at tip of the needle of the compass on the cardboard. Mark the point on the cardboard at the tip of the needle of the compass. So once you have marked this point at the tip of the needle, what you have to do is uh, now you can say move the plotting. I'm writing it as compass to save some space. Now move the compass such that the end of the needle is aligned to the marked point. Okay, mark point, then mark a new point corresponding to the tip of the needle. Okay, um, as you can say shown in B. Okay, so these are A and B. Uh, so then repeat the procedure till uh, the compass aligns with the starting point. Uh, then join the marks together for the magnetic field line. Then repeat the procedure um, you can say uh, at different locations on the cardboard. Okay, so this is how I would say that you will be able to draw the complete magnetic field lines or magnetic field for the uh, this current carrying conductor uh, that is passing through a cardboard. Then in the last part it says state what else the student can deduce about the magnetic field in this investigation. So the direction of the magnetic field can be obtained from this magnetic field, as I've told that if the thumb is pointing towards the direction of the current, the curved fingers will be pointing towards the direction of the magnetic field. So the direction of the magnetic field, it can be either clockwise or it can be either anti-clockwise. Similarly, the strength of the magnetic field can also be deduced if the magnetic field lines are very close together or closely packed together. It means it's a strong magnetic field. If it is far together and as you move away from the current carrying conductor, uh, the the compass points are not you can say well defined, or you are getting uh, way you can say sometimes you're getting a point, sometimes the compass needle is not behaving properly. It means that the magnetic field lines or the strength of the magnetic field is pretty weak. So what else, student? uh, the direction of the magnetic field that is clockwise or anti-clockwise? Can be obtained, or can be, you can say, deduced. Uh, the strength of the magnetic field can also be, you can say, obtained, or can also be, commented upon using this technique. Okay, so this is how you can write this answer, and again you are free to use your own choice of words, and just like that. And this is the last part of this exam. So I thank you all for listening, and thank you all for supporting my channel, and I wish you best of luck for your exams and all the best for your future endeavors. Thank you. Take care. Bye bye.